Hello folks, Rashid here. Thank you so much for joining. This is another video in the series of full chip timing. And this video is going to go public, so I want to give you a very quick overview of this series before we go into today's topic. Today's topic is looking into isolation cells and retention cells. So we are on the UPF stage right now, reading UPF. But anyway, this is the second timing series, the playlist that I call on YouTube channel that I'm building. The first one was for the block level STA. And we covered a lot of theoretical concepts, flows, methodologies for the block level flow. And this one takes that whatever we build in the first series, the playlist, to the next level, where we are looking into the full chip level, where you don't have just one block, you are reading so many partitions or blocks and building a full chip. So focus here is, the very first focus is, okay, how we are building gradually full chip timing flow. And my focus is on the concepts, right? And the methodologies, the theory behind, so that if you understand that, then whatever tools you are using in your college or at the job, you can understand the flow and methodologies behind, the key concepts behind. So that's really the focus. But I will definitely share some of the examples, commands using any STA tool. Okay, so we are building full chip timing flow first. So once we build that, the goal is also to understand each stage. For example, right now we are at the UPF reading stage. And when I didn't say, okay, we just read UPF and then moved on, since I didn't give any background on UPF prior to this on my channel. So I'm going into multi-VDD power domain. I first explained, okay, why we need multi-VDD domains and why low power, what are different low power techniques that we use, and among them multi-VDD or lower VDD for certain cells is one, and then we can shut down certain areas and keep the other areas running, and that makes the use of some other things like level shifter and isolation cells, retention cells. So in the past few videos, I have explained the level shifter cells. Okay, so we went into detail. I showed even some of the circuits there just to remember the core concept behind. And today's video will be about a couple of other important things there. And then I'll show an example of a UPF file. I believe that once I explain you the core concepts of a UPF, which is there to describe the power intent of your design, which can be used by implementation flows as well as can be used by verification flows to check. Here we are using a verification flow. So I believe once you understand the key concepts there, then the rest of the things inside the UPF file is just some syntax thing, right? How you define different things. And we will go over that in the next video. Okay, so yeah, so we are building full chip timing flow. We will look into analysis at top level, which is where it's the different thing comes in, because now you have to deal with so many blocks, and maybe sometimes you have to spend more time on interpartition timing analysis. And we will also look into budgeting, IO constraints, and all that, hierarchical analysis versus flat analysis. What are the key components there? Context, boundary model, those type of discussions we will have there. So, and a lot of other things that I haven't mentioned right now will bring into full chip timing series. I don't know how long it will take, but we will build a very good resource for you guys so that you can have a very good understanding and you can become a full chip timing owner on your chips in future. Okay, so that's it. This is, by the way, for the members. Membership is very reasonable, the lowest I could get. And in US, in Europe, I think is this one, but in your country you should check. I think in India it's about probably 80 Indian rupees a month. And yeah, by the way, you on the mobile app, you cannot join it for some reason. You have to open on desktop, laptop, YouTube channel, my channel, and then click on the join. All right. Okay, so let's get started. So today's topic, oh, where I put it on the wrong place, that slide. But anyway, I already explained you that level shifter I have explained. Okay, when you have a one power domain, which is, let's say here in this case, I think we have been using 0.6 volt, but if 0.6 volt and another one is at 1 volt, right? Then these are to add two different voltage levels. Okay, this is where one voltage comes in, another voltage comes in, and they have the same VSS. So for reliable operation between these power domain, we studied level shifter last time in both sides, from low to high, high to low. The other potential problem is if our power states are such that this all the cells in this power domain or all the cells in this voltage area, remember voltage area is more physical and power domain is more logical. So if this power domain is off and this is still working, then we have a potential problem at the interface. So the signal here, okay, since this inverter, which is a PMOS and NMOS, remember, PMOS connected to supply voltage, NMOS connected to ground. So at this point, there is no low impedance path or no direct connectivity to VCC on ground. So this node is floating. And floating node is a problem in our circuits. Why? Because this inverter, this PMOS and NMOS, I don't know if this voltage level, whatever left voltage or floating voltage level, there will be considered 1 or 0. And incorrect value can come into this flip-flop and can propagate. That is a problem. If the right value goes, great. But if not, then it's a problem. It can change the functionality of the design. Understand that? And even in our physical design, sorry, in our circuits, in our databases, and a cell where output is not connected, dangling, that is okay, right? It's not driving anything. But the input we cannot leave dangling. We have to, you have seen that tie off, we have to tie it off. Connect to so tie off, tie high, or tie low. You need to put 1 or 0 on it. So you need to connect, if something is floating, you need to connect to supply voltage or need to connect to ground. And for that, we use tie high cell, tie low cells, depends upon what voltage level you want to connect. And also tie high, tie low cell kind of inverter buffer, but it's okay, we don't go there, but basically you want to tie it off, right? It's the same concept here. You want to, when this is off, you want to tie it off. You want to tie it off 1 or 0. It depends on what you want. And that is the decision that RTL owners need to make, architects need to make. So they are going to define the isolation scheme for us. Whoever defines the UPF, by the way, first used in the simulation and then comes to the same UPF comes to the physical design, first in synthesis. So before the isolation cells can be put in the implementation tool, in the place and route tool as well as in synthesis tool. I have used it in synthesis tool. So your synthesis started with an RTL that doesn't have isolation cells in it, but the UPF described that, right? And based on the UPF description, synthesis tool adds an isolation cells on those interfaces. It knows, okay, where those crossings are happening, and then it puts isolation cells. So isolation cell is what? It's just an AND gate, could be an OR gate. So look at this one. So all it does is, in an AND gate, you can force this to 0 if the enable is 0. Doesn't matter what logic comes here. This is disconnected. This has the connection there. Okay, so if you really want to put 0 here, when this is off, put an AND gate, put this bit 0. Now if you want to put this 1, you cannot have AND gate and put 1 here, right? Because if this is 0, it will force it to 0. then you need OR gate. And the other important thing is, okay, this enable need to come from somewhere which is kind of have a valid supply voltage. When this is off, you don't want to power management block, you don't want to have inside. This is typically power management is all part of always on. So in this example, this can also be shut off or shut down. And in that scenario, we need another third voltage level, which is always on. It's always stays on. And that's where I mentioned previous video that your power management or your clock generation or some other signal which need to be on all the time, they need to be in that voltage domain. Okay, so that is one thing. This is coming from power management. This color is for always on. The other thing is the supply voltage for this AND gate. This AND gate, two PMOSes, two NMOSes, two PMOSes in series, two NMOSes in, two PMOSes in parallel, NMOS in series. They need to be connected. The PMOSes need to connect it to be a supply voltage. You cannot give this supply voltage, right? Otherwise, this will be, it's the same problem here. So you need to connect this to a supply voltage, which at least kind of stays on when this guy is on, right? So if this is good, you can connect this to this, or you can, I think if in this case, you don't see any problem, I think conceptually this can be connected to this supply voltage. When this is on, at least my management signal here comes on. But again, those are the things how to do this. This is more like RTL architecture, folks. They're gonna make that decision based on the logical requirement. Okay, for you in the timing flow side, you will have these isolation cells in the actual standard cells. So these are special standard cells, just like level shifter, which are part of your standard cell library. So they will be there, and they will be in the netlist, and then you read the netlist, use the link, and they will be connected to the relevant standard cell in the library. Okay, and again, in majority of the flows that I've seen, you're not dealing with supply voltage, right? In your netlist, in the library you have a related supply, but typically your netlist doesn't have a supply voltage pins in the instance of the cell. Now we will look into that. I think there are flows where you can have a supply voltage pins in the netlist, but generally you can skip that, and using this UPF we know, okay, which what cells are in what power domain series. Anyway, what was I thinking? I don't know what was I thinking. I was thinking of explaining you something and I completely forgot that. All right, so isolation cells, done, understood? Okay. As I said, it's just an AND gate, so it's not a complex circuit. All right, so now we go to the next step. Okay, I was thinking, so if you have, let's say I can show you. So if you have a requirement that you need to put an isolation cells and level shifter between the design, I just create this situation, theoretical situation. Then which one you put first, right? The level shifter input need to be, if this is floating, everything will go floating if this passes. So you need to have a proper signal there. So you need to have a isolation signal before that. Now when this situation happens, if this is always on, this level shifter basically is level shifting from always on to high, not from this voltage high. So connectivity of these two is also important in that way. You also need to look into floor plan, but again, we are in the timing side. So for you, if you're a designer, you need to ensure this. But again, in the timing netlist, you will have these things correct. Your netlist already, somebody has run formal equivalence on it. Somebody has run kind of UPF testing. I think in even conformal low power, you can also check things on the UPF side, or tools like Spyglass. You can also check the connectivity on isolation side, level shifter, and all that. So those will take care from the timing side. The netlist, whatever comes, so you just time it. Okay, that is done. What do I want to show here? Oh yeah. So the second concept is, which is the third concept, level shifter. Then you have isolation cells. Then you have retention cell. Retention. I think the retention cells. So these are typically the registers. So let's say this power domain is off. Okay, and this circuit over here need an input from a register in this domain. They need to know the state of this. Now, if you turn this guy off, then this will be what is it, off, 0 or 1. Okay, but it's not that it has to be 0 or 1. They really need to know whatever is the logic state of that. So for that reason, some of the cells we need to retain their logic level before they were shut off. So that's where these retention registers occur. So these are specially made registers. So register, there's a master, there's a slave, right? You first on the one logic level you write here. On the next level comes here, you read from here to output. That's where it appears as if you are reading on the edge, but actually you are writing and reading from the levels. Remember the flip-flop master-slave structure? So what they do is actually this cell, the retention cells, your master is on the same voltage at this power domain. Your slave, what happens is your slave need to be on. So anything that needs to be on a supply voltage that stays on when this is off. So this represents that. So what happens is you have a slightly different connectivity. This retention cells overall, if you look at it, this is a flip-flop which is getting two supply voltages. So this always on supply voltage is connected to the slave. So in that case, what happens is even with this goes off, this stays at a particular logic level. Now, whether they add another isolation cells in the beginning or not, but they need to ensure whatever is required to ensure that whatever the logic value of the Q was there before, it just stays there. So that's what I'm representing with this yellow. So yeah, retention flip-flop, isolation, level shifter. I think those were the initial concept that we have covered. So next time we will look into an example of UPF. And after that, we will move on to the next stage of our timing flow. All right. Hopefully this video was useful. Please let me know in comments and giving me your feedback. All right. That's it for now. See you next time. Bye.